if we look at some code written in ML or any language of the ML, we often observe very similar functions. For example, here we have the addition and the append function. And these two functions have a very similar structure. For example, if we take all the constructor nil and replace it with 0 and replace const with the successor and remove the elements of the list, we get the addition function and the append function. And indeed, these functions respect some kind of coherence property, which is that the sum of the length of two lists is equal to the length of the concatenation of the two lists. This is not surprising. And we have a link between the two data types. So natural numbers and lists. There is a successor constructor that is similar to const. 0 is similar to nil, and indeed they have the same recursive structure because they have the same recursive variables. And this link can be expressed with a very simple projection function, here length, that only removes the information and translates the name of the constructors. So in general, our motivation for this work is that we often have very similar data types. For example, trees with nothing and trees with something at the node, or lists and vectors which are listed by their length. And this leads us to writing very similar functions because the types have the same structure. And so how can we automate the work of writing these functions? And Ornaments are a solution to this problem. They were introduced by Thomas McBride and Pierre Daillon and some of Ornaments. And so what we are interested in is implementing ornaments in ML. So ornaments were developed in type theory using descriptions and things that are not available in ML. And so we want to adapt them to ML. And I described here some little implementation prototype of ornaments. It doesn't work directly in ML, but in a small systemF-like language. But it adapts easily to ML, and we will use ML for the example. So we introduce a syntax for ornaments. So we say that ornaments were types with a very similar recursive structure. And we define them by a projection function from an ornamented type, here lists, to a Baire type, natural numbers, that can forget information, rename constructors. And we have some syntactic restrictions that ensure that they preserve the recursive structure. And so we have a system, we declare an ornament. So we say that length is an ornament from lists or from natural to lists. And it is a projection function, so we write reverse type. It projects from lists to natural numbers. And this is checked by the system. So it checks that the recursive structure is preserved. And that defines an ornament. And then once we have defined an ornament, we can try to lift functions. So we saw the coherence property for append and add, and we can generalize it to any function. So the projection of a lifted function applied to two arguments, for example, should be equal to this function applied to the projection of the arguments. So the projection commute with the function. And we will use this as a guide to lift functions from the Baire type to the ornamented type. It is more interesting than doing the reverse, but because we anticipate that there will be many ornamented type on top of one Baire type, and the reverse is not true. It's kind of not true. So here I'll describe the process we use to lift functions. We call this the syntactic lifting because it respects the syntax of the function and tries to stay as close as possible. So we have the addition function, and we want to lift it. So we write a lifting specification that And here we say that we want to generate the append function by using the ornament length on each argument. So from this, we want to have a certain coherence property, which is this one. So I've written n arrow nl instead of n equal length nl because we will, it's simpler to write, and we will use it in the other way to lift the functions. For example, nl is a lifting of n. And this is a rule that expresses the coherence. So now we want to copy the structure. We copy the declaration of the function, renaming the argument n to ml, n to nl. And we learn that ml is an ornament of n, nl is an ornament of n. So we continue, we copy the pattern machine. And we have n that appears here. And we know that ml is an ornament of n. So we will put ml there. And we continue. We have the patterns. And until now, we have completely ignored the structure of length. But to translate patterns, we have to look at the code of length. And we get two rules. One says that nil is a lifting of 0. And the other says that something nl is a lifting of successor of n if nl is a lifting of n. So we apply these two rules in the other way to translate the patterns. So 0 becomes nil, successor becomes const, and we learn a new fact. It is that n prime lifts to ml prime. So we continue going through the code. We have n translated to nl, and we have successor of add n prime n. The successor translates to const. And now the hypothesis says that the argument of S must be lifted using length. And we have the coevent that says exactly that append ml prime nl is a lifting of add n prime n. And we missed something there. And here's the result. So the syntactic lifting gives us this function, and we are missing something because the ornament only tells us about the things that are already in natural numbers, and the elements are new in lists. So this is the creative part of ornaments. We have to decide what to put in place of the question. And this is kind of an orthogonal problem. And we have three possible solutions for this. One is to just let the programmer put x there. Another way would be to write a patch alongside the listing specification. And we could do some code inference. For example, x here makes the most sense because it has the right type and it is immediately in the context. We have generated.
Isn't it in the only solution because of parametricity?
No, it is not the only solution because we could go further in the list to find another element if the list is not empty.
Right.
So this is not something we can really do automatically and uniquely. Coevents, the property we explained before, is in fact not enough to limit the results of the lifting. For example, here we have the ref append function that does the same thing as append but reverses the first list. And it is also coherent because the length of a reversed list is equal to the length of the original list. So we have a coherence condition that helps us for the lifting, but it is not enough to get the automatic lifting, and we have to add the condition that we follow the syntax of the original function. And now I describe some applications. A first application is using ornaments for refactoring. So, for example, in compilers, we have some very small language with constant addition, multiplication. And we have written some functions in this language, for example, evaluation. And we might realize that it was not the best representation of expression, and we want to factor binary operators into a single constructor parameterized by the iteration, so like x prime and so on. And ornaments can help us not to have to write the eval function again. So what we can see is that x prime is an ornament of x because we have this very simple function that projects our new expressions to the old expressions, and it is a valid ornament. And then we can ask for lifting eval prime of eval using our ornament com, and we get the function we wanted. So this is exactly the code we could have written manually, but it's written automatically. And the lifting in this case is unique because the conf function is bijective. So the coherence property defines completely eval prime. So this is a case where ornaments work very well. Another case, so we have seen that we can lift some simple data structures, for example, natural numbers to lists, but it can also be done for more complex structures. Here we take the example of sets, represented by binary trees, and maps, which are sets, with a value associated to every key. And there is an ornament from sets to maps, because we can project maps to sets by forgetting the value and getting the set of keys. So it's a valid simple ornament. And we can use it to lift function. So we applied it on the set library of OCaml. Here I take one of the most interesting example, where we lift an higher order function. So we have the function exist that takes a predicate p and a set and checks whether there is an element of the set that satisfies the predicate. And we want to lift this function to maps. The thing is, to have a useful function of maps, we need to give an additional argument to the predicate, which is the value associated with the key. And so we write this lifting specification, and you have plus alpha there that says that we want the function to get an additional argument. And this is the predicate key. And this is an higher order function. And we ask for the lifting, and we get this result that looks like what we want to write. So the only thing that's missing is giving the value to the predicate. And why is it missing? It is because, once again, ornaments don't say anything about value. So the programmer has to fill this part. In fact, when lifting the set library of OCaml, this is in fact, the result on all functions. What's missing is expressing the flow of values, values as in the values associated to the keys, and all the rest, which is the non-creative part, because it's already not done on set, is done automatically. Ornaments are also interesting in GADTs. So if we have, we often have several data structures with the same contents, but different invariants. For example, we can have lists. On top of lists, we can have vectors, or non-empty lists, lists of even length. And so we have many data structures built on a single one. And often, writing a function on vectors is very similar to writing the same function on list. So we would want to do that automatically. So we have the definition of lists. Vectors are indexed by 0 or something. And vectors are an ornament of lists because we just have to forget the additional structure that is given by the GADT environment. so we have this function. Here we have to write a type the type of the projection function because it is polymorphic recursive. And since the function only the ornament of vectors only adds logical information but no new content, we would want the lifting to be unambiguous. And the listing for GLDTs works partially. So it is automatic for some invariants. We have the zip function there that zips two lists together while checking that they are the same name and fail otherwise. And we can lift it to vectors to a function that doesn't fail because it takes two vectors of the same name. So here we have to write the type when asking for the lifting because the system can guess the invariant we want to lift. So we write the type and say that we want to lift every argument and the result with the element to list. And we get the right function. Almost, because there is one case that remains is the case where the two lists have different length. Why? It is because currently our implementation is able to deal with GADTs, but in fact doesn't look at the GADT invariants and only at the non-GADT part. So it can detect that this case is new. And in fact, this creates some problem because it can lift a function, but not do all the work the logical work, the proofs are not done by the system. So sometimes the lifting is not well packed. So this kind of thing can also be used in compilers, not only with GADTs, but in fact, if we remove this constructor from a type, it is an ornament because we can project all the other constructors to the constructors of the first type, and so we can create restricted version of types and check that the functions will and that this subset will be stable by the function. So that could be useful, for example, in compiler writing, like in this case, this one. And so in conclusion, we have learned that describing ornaments by projection is probably the good way to do it in ML. So we have observed several useful classes of ornaments: refactoring, GADTs, lifting data structures. We have described syntactic lifting that gives good results and predictable, but there's still some things to do. So one thing is that we don't really understand why the syntactic lifting is good. We have an operational understanding of it, but no completely semantic understanding. Another thing is that I have mentioned the language of patches that would be used to fill the missing parts. And so we have a very simple language, but we might want to have some more powerful patches. For example, we could give some properties that we want the function to respect and try to use them to infer the missing parts. And we also would want patches to be stable by modification of the original code, or at least robust. There is a question of how to integrate this into ML. So it works mostly, but we have some questions about effects. So we don't say anything about effects yet. And how to mix it with type inference. Because so type inference could be useful to get a better lifting, because lifting in fact does some kind of type propagation, whereas the type is in fact the length of it, for example. And there is a question of how to combine ornaments. For example, we could have two geometries on top of the same base structure that have different invariants, and we could take the intersection of the two types, so a type that respects both invariants. So thank you for listening.
Thank you, Thomas. So I just wanted to point some things that, especially when Bruno Oliveira made his talk this morning, he mentioned ornamental algebra as an orthogonal dimension for modularity. And looking at Thomas' talk, I see two patterns in which you can use ornaments. So the first one is when you have this projection from list to mat. Here you're preserving the recursive structure, and the ornament is adding extra information. And then Thomas also had these other examples, for example, where you have a compiler that might have some lead desugaring. So you start with, you have a language that is augmented with some more cases, and then you can also do a projection from the smaller language, so the language without lead, to the language with lead by just injecting everything. And this reminded me of Bruno's example where he had this expression language without negation, and then you can think of negation as a desugaring. So here in this second kind of projection, where you're actually projecting into something that has probably even more recursive structure, it feels like there's a similarity as well with the goals of what algebra, like the F algebra are doing. So there's this core ornamentation which is about adding fields to recursive structure, and then also this way of projecting the sugaring. So I'm wondering if you think there's a deeper connection between these two dimensions.
I think they are somewhat different. What is, in fact, ornaments are implemented as a kind of preprocessor. So maybe we avoid all this question of will it be well tied because the property is preserved or not, because we just check this at compile time and in fact try to prove that the function has some properties. I guess that one of the with algebra, you can do that during typing or really in the language and not before analyzing it.
Are there other questions?
So the projections you use, they look very similar to the abstraction functions in abstract interpretation.
Yes, there is probably some similarity. We can. There is probably also a concretization where you take all the values that project to something, and they should have a nice shape because they are really recursively defined, and it's just we ignore some fields. So there is probably could probably be interpreted as abstract interpretation.
So it appears to me that the language ornament that you are implementing here is a bit weaker than that presented in the 2012 paper. So I'll just say what I think is missing, and I will check with you if I'm right. So in the 2012 paper, you could compute ornaments out of indices. Therefore, reindexing didn't have to be unambiguous. And I think you made it weaker here by not having this feature.
So you mean, yes, rebuilding index by proving that there is only
So in the original paper, there was an example of building vectors by only allowing certain constructors if provided with a certain index, and they called it computing on an index.
Yes. Yes, I think we can't really express that. Not as simply, at least because we are. I think the point of computing on index is that you could directly, if you knew you would only have a value of a certain type, even if it was wrapped into a constructor, you could directly put the value.
But you could also extend the ornament based on indexes with certain additional fields under certain indices, and under different indices you would keep the structure intact.
With OpenWGP, you have some kind of computing of indices, but it's written the other way. So you have to, from a constructor, you generate. You take some. I think that it's just a difference between expressing things as inductive families and somewhat recursively defined types. If you compute on indices, you in fact define a recursive function from natural numbers to a type that is a type of vectors of this length. And here with GADTs we have something closer to an inductive definition that is indexed by the number, but you have a constructor that takes a number, a vector of this length, and builds a vector of size the successor of this length. So I think this is just a different flow of indices inside the code, but I'm not sure.
There was another question.
So I thought the refactoring example was interesting, but I have a question about it. Normally when you do refactoring, you want to throw the old code away and keep the new code. So in here, I think what you're suggesting is that you have the old code, a new code, and some conversion between them, right? But it raises a question in terms of maintenance. So let's suppose, compilers, they do evolve. People do changes in the compiler. So let's suppose you want to modify the pretty printer. You have to modify the two places?
There are two questions. I think the first one is, can we replace the code by the new code? And the answer is yes. We could do a tool
right.
that we remove the old function and reuses the name, so preserving some kind of interface. And yes, it would be a useful tool for the program. The other one is how to maintain the lifted code if we change the base code. And it is a real question. We have the same. That's one of the problems could maybe solve with using patches, a good language of patches that would describe what we want, but not be too dependent on the exact syntax of the original function. But it is true that for example, addition, if addition function and natural numbers were changed to a tail recursive version, the lifting would be the rev_append function that reverses the list and not the original function. So there is a problem of synchronization. So I think patches are part of the answer. I'm not sure that is also the question.
So we're 3 minutes over time. Was there one more question? Or?
Very quick one. So when you had the rev_append example, did you also ever extend the patches language to be able to talk about the logical parts instead of just the?
Not really. For now, it really follows the syntax of the original function. You can, at some point, say, I don't want to follow the original function anymore. But rev_append is, in fact, completely different function when we look at its code, at least. So I don't think it's easy to do something like this.
Anyone else? Okay, let's thank the speaker again.